Okay, we're going to cover chapter 1, part 3 in this video for pre-calculus. Camera angle here. Share the screen. All right, and the first thing we're going to talk about is a quick review of the most important ideas in the first two sections in chapter 1. First of all, function versus a non-function. Remember that a function will pass the vertical line test and a non-function will fail it. So if a vertical line ever touches 2 points, then that is not a functional relationship. Even, odd, neither. So remember that even has symmetry about the y-axis. Odd has symmetry about the origin. And neither will have neither of those two things. Like so, maybe. All right. Now, Wednesday, I'm going to have posted a quiz over the first two sections. So by this point, you should have taken the quiz that I put up on Wednesday. All right, so part 3 is about continuity in behavior and limits. So first of all, continuous function. There are a lot of fancy definitions that use a lot of mathematical shorthand that you've never seen before. So instead of that, I'm just going to give you a simple language definition here. It's something that can be graphed without picking up your pencil. So you can graph it and you never have to pick up your pencil. In other words, the line is continuous. So a limit is a value of a function, well, of a relation. It doesn't necessarily have to be functional. The value of a relation as x approaches a certain value. So there are pretty good reasons why we wouldn't want to go all the way to a certain value. Let's say division by 0 occurs at that point, so it's mathematically impossible. But you can get arbitrarily close to it, and we call that evaluation of the function. As we approach a value, its limit. So a discontinuous function cannot be graphed. Without picking up the pencil. And then an infinite discontinuity, a jump discontinuity, and a removable discontinuity. So these are three ways that a function might be discontinuous. We talked about having to pick your pencil up when you're graphing it. So these are three ways that might happen. So an infinite discontinuity means the function goes to positive or negative infinity, or both, around a certain discontinuous. So there's the x value that's problematic in this case, and you see how the function goes to both positive and negative infinity around it. It can go to positive infinity on both sides, negative infinity on both sides, but it goes either to positive, negative infinity, or both around a certain point. And we call that an infinite discontinuity. A jump type discontinuity, these occur exclusively in piecewise, like we described in chapter 1, part 1. And they look like this. So you see how the y value jumps to a different point and then continues on. So that's a jump type discontinuity. Again, only occurs in piecewise functions. Pretty unusual. You won't encounter that one in the wild very much. Okay, removable type discontinuity. So this is also called a hole type, H-O-L-E, hole type. But it looks like this. So you have an otherwise continuous function and then an empty spot. And these are tricky because sometimes we'll graph them on a calculator and it's only a single pixel missing. And it'll make you think it's a continuous function, but there is a tiny little hole type or removable discontinuity. So non-removable describes the other two types. So the jump type and the infinite type are considered non-removable. So jump or infinite type are considered non-removable discontinuities. And then this is kind of redundant. We've been talking about these. So this is a point where you will have to pick up your pencil to graph a function. So it's an x value on the graph where you either have to jump, go to positive and negative infinity, or you will have a hole. So you'll have to skip a point. In behavior. So this is a description of what the f of x does as x goes towards positive or negative infinity. So as x gets infinitely large in the positive or negative direction, what is f of x doing? That's the question. All right, moving on here. Limits. So you'll see this limit notation here. So this is probably new to you guys. And if the value of f of x at a point is what we're concerned about, the limit describes the behavior as the function gets arbitrarily close to that point. So as it approaches C, not as it actually is C. And you might think, why in the world would we care about that? We'll just look at what the value is at C. Well, yeah, maybe C is not defined for some reason or another. Maybe there's division by zero at C. And in those cases, the limit is the only way that we can understand what happens at that point. Okay, so here's your book's take on infinite, jump, and removable discontinuities. So we already discussed those, but your book has a nice graphic here. So in order for a limit to exist, we need to, well, first of all, let's do what's called the continuity test. So the continuity test is a test to see if a function is continuous at C. So basically all these three things, which are, it's defined at C, the point exists, it approaches the same value from either side. In other words, the limit exists, and the value is equal to that limit. So all these things just mean that I don't pick my pencil up when I graph that point. So think about it like this. If this is the point we're concerned about, if I can just graph through it like so, then it is continuous at that point. If for whatever reason I can't do that, let's imagine this scenario, well, that's discontinuous at that point. So if this would fail the continuity test at this point, this would pass it. One on the left would fail, the one on the right would pass. Okay, so let's mess around with this a little bit. Determine whether this is continuous at x equals 1/2. So the way we're going to do that is we're going to say, first of all, does f of 1/2 exist? That was the first part of the continuity test. So if I plug this in, 1 over 2 times 1/2 plus 1. So that's 1 over 2 times 1/2 is 1 plus 1. So it is 1/2. It does exist. There's no division by zero or anything else that happens at that point that would cause us concern. So the function exists. It passes the first part. Now the question is, does it approach the same value from the left and right? So in other words, if I say this is f of 0.5, So if I say 0.49 and f of 0.499 and f of 0.49999. So if I'm getting really close from the left, and this would be just a little bit to the right, let's add a couple more zeros here. So I'm concerned now about these values that are just to the left and just to the right of 1/2. And we'll see what the function's values are at those points. So if I plug into my calculator 1 divided by, and then in parentheses, 2x plus 1. And then I go to the graph and I plug in 0.49. So I need to put trace and then 0.49. So it tells me it's 0.505. And then let's try 0.499. 0.5005. So this was about and then this last one I put in here, 0.4, and then 4 nines. So 0.500005. See how it gets closer and closer to this 1/2? So these two values are the same. The only question is it the same on the other side? And this may seem kind of like common sense. Well, heck, I can look at it and tell that's the case. True, because this is a pretty simple example, but that won't always be so. It will sometimes be the case that you cannot tell by looking. This is an example where you can. But anyway, we'll punch in 0.51 and 0.5001 and 0.500000. Let's see, no, too many. 0.500001. And we see that's 4999995. So we see that as also approaching 1/2. We see it's closer and closer to 1/2 from both sides. So it passes the first part of the continuity test, the function exists at that point. It passes the second part because the limit exists. In other words, it approaches the same value from both sides. And then it passes the third part because the value that it approaches, the limit, is the same as the function's value. So a really complicated way, super complicated way to say something very simple. Can I graph it without picking my pencil up? Yes. And so all these things are true. All right, so this is a graph that shows the values of the function as it approaches 1/2 from the left and right. I did this on the previous page, but this is a nice graphic demonstrating that. So let's talk about the following function. So pause the video here, see if you can figure out whether this is continuous at 1, and then come back. Okay, so I'm assuming you're back. And here we find, so f of 1, first let's see if the function exists at that point. So I have 1 plus 2 minus 3. 3 minus 3 is 0. It does exist. 0 is a value. That doesn't mean that it doesn't exist because the function evaluates to 0. It does exist. It has the value of 0 at 1. So passes the first part. And then if we take our calculator and do the same process we did on the previous example, you get closer and closer from each side. In other words, you'd go 0.999 and 1.0001 or whatever. We'll see that the function gets closer and closer to 0 from each side. You can also look very carefully at the graph and see that through this point at +1, You will not have to pick your pencil up, and so this is continuous. So a test for continuity. Functions are not always continuous. So here's an example, and you could probably look at this expression, 1 over x minus 1, and see that we're going to have a problem at x equals 1. So in the first example, they both passed the continuity test. But here, if I plug in 1, so f of 1 equals 1 over x minus 1. I'm sorry, f over 1 minus 1. And so that's 1 over 0, which does not exist, has no solution. You can't figure that out. So if it is discontinuous, which is what we find, what type of discontinuity is it? Well, the best way to do that is going to be to look at the graph. So let me share my whole screen as opposed to just that window so you guys can see my calculator for this one. Okay, so the best way is going to be to graph it. So if I say y equals, and I punch in 1 over x minus 1, make sure and use your parentheses here, and I graph, we're concerned about its behavior around positive 1. Now you'll notice this line that's between those two halves of the graph, that's a mathematical artifact. In other words, that's because this calculator is not great. If I used a better calculator, and let me do that real quick to show you what that graph really looks like. So from this point forward, you can understand what the calculator means when it says that. So if I go to Wolfram Alpha, and I graph y equals 1 divided by x minus 1, this is a much better calculator, and it gives us this graph. And you see how there's no line in between those two right here, like there was on the calculator. So this line right here is a mathematical artifact. It's a consequence of the calculator doing a poor job with the discontinuity. Okay, so anyway, this is the real graph, and we see that it is clearly the infinite type. So based on graphical analysis, this is a discontinuous and an infinite type discontinuity at x equals 1. Okay. So investigate function values close. So if we took, and remember I said to punch in your calculator, closer and closer to positive 1, you'll see that it goes to really different values. And this is a case where the continuity test actually makes sense as opposed to that first example. Negative 10, negative 100, negative 1,000, and bigger and bigger and bigger. In other words, it's going to negative infinity, or down in this case. And then here, 1,000, 110. So as we approach 1 from right to left, it's going up, up, up to positive infinity. As we approach from left to right, it's going down, down, down to negative infinity. And we saw that on the graph. Here's that graph. So what about this function? X squared, I'm sorry, f of x equals x minus 2 over x squared minus 4. X squared is going to behave in such a way as to make this a little difficult to understand just by glancing at it. But anywhere that the denominator is 0 is going to cause us a problem. They want us to test x equals positive 2. So if I plug into f of 2, I get 2 minus 2 over 2 squared minus 4. So that's 0 over 4 minus 4, and that's 0 over 0. Once again, that does not exist. That's a discontinuous point. So if it doesn't exist, we know it's discontinuous at that point. And identifying the type is going to be tricky here, because if I graph it on my calculator, or even on Wolfram for that matter, it's going to look continuous, at least at that point. So let's see here. X minus 2 divided by x squared minus 4. So if I graph this, so at -2, it's an infinite type, but at +2, it looks like it's continuous. However, if I hit trace, 2, enter, you see how the y is blank? That indicates that it is a hole at that point. So this is a removable type or hole type discontinuity. And I'm going to try to zoom in close enough so that you can see that empty spot. So if I go to the window and I change the x-min to very close to 2, let's say 1.5, and x max to 2.5. So that's going to zoom in on that part of the graph. And if I change my y-min to 0 and my y-max to 1, and then hit graph, I'll see this. And do you see that little tiny hole that occurs at x equals 2? So it is a removable type, a hole type discontinuity. That one's pretty tricky. So if we plug in values, we see that it approaches 0.25 as it gets closer to 2, but it is undefined at 2. So this is a case where the limit exists, but the function's value does not exist at that point. Okay. So here's one for you. Take a second, work this out, and pause the video, come back when you're finished. Anybody? Yeah, help yourself. All right, so I'm going to assume you're back, and let's talk about this one. So we're concerned about the function's value at a +1. If you test it at 1, it's 1 over 1 squared minus 1, which is 1 over 1 minus 1. And once again, we get a denominator of 0, indicating that it has no value. It's not defined at that point. So it is discontinuous. And to identify the type, we need to do a little graphical analysis. You can hit zoom in 6 to always set your window to the standard window. So 1 divided by x squared minus 1. If I hit graph. Ooh, that's weird, isn't it? We're concerned only about this part at 1. And we see that as the infinite type at all those discontinuous spots, including +1. It is an infinite type because the function goes to positive and negative infinity around it. Okay. Intermediate value theorem. So if you got a continuous function, and between two domain values, it assumes one value f of a and one value f of b. If it's continuous, it's going to hit every point between those. That's basically what the intermediate value theorem states. So think about it like this. If you're 5 foot tall when you're a freshman, and you're 6 foot tall when you're a senior, then you have hit every point along the way between 5 and 6 foot at some point during your high school career. So this basically just says that if you go from A to B, and your starting value is f of a, and your terminating value is f of b, then between A and B, there will be some C where you've hit every point in between f of a and f of b. So the intermediate value theorem. If I weighed, 220 pounds today and 230 pounds a year from now, then at some point over that year, I will have hit every single point between 220 and 230. If that helps you understand it. Okay, example 3 is about approximating zeros. So determine between which consecutive integers the real zeros of the following function are located on the interval -2 to 2. So these are the x values we're concerned about. Only those that go between -2 and 2. So let's use the calculator to do a little graphical analysis here. So if I punch in x squared minus x, x squared minus x minus 3 divided by 4. And then I want to go from -2 to 2. And let's go -2 to 2 on the y as well. Oh, I know what happened. You have to use this, oh, I left off the exponent. Never mind. Now let's try it. All right, good. So you see the two zeros here. So the zeros, in other words, the x-intercepts, occur in one case between -1 and 0. So between -1 and 0 is 1, 0. And between 1 and 2 is another 0. So those are the consecutive integers between which the x-intercepts or the zeros lie in this function. And we found it by graphical analysis. All right, here's the graph again, and it's a more zoomed out version of the graph. Once again, you can see between -1 and 0 and 1 and 2, we find those zeros. Okay, so what about this function? So x cubed plus 2x plus 5 on the same interval. So we'll just go to y equals, punch in x cubed plus 2x plus 5. Big graph. So only 1 0 occurs between -2 and +2, and it is between the consecutive integers, -2 and +1 on the graph. So between the x values of -2 and -1, I guess I'm +1 a second ago, -2 and -1, this is the only 0 that occurs on this interval. Might be other zeros there, in other parts, it might not. But there's only a 0 between these two for this interval. Okay. And this shows the graph zoomed out, so we see that is actually the only 0. This is something to be careful about with your textbook. Notice how this is indexed differently on the x-axis, and actually it's wrong, I think. Yep, it is. So you have to be careful. Your book even outsmarted itself because it re-indexed the x-axis, but it didn't change the graph. So your book goes by 2's on this graph. It indexes by 2's, and they confused even themselves with that, because here's the real graph. X cubed plus 2x plus 5. Yeah, that's right. So this is right. This is wrong because it doesn't happen at -3, which is what this indicates. It happens between -2 and -1. So anyway, this graph is wrong. Your textbook made a mistake there. Okay, so determine between which consecutive integers the real zeros of the following expression are located. And this time we're worried about between -4 and +4. Once again, pause the video, see if you can figure this out, and then come back. Okay, assuming you're back. We go to y equals, clear out whatever's there, and punch in x cubed plus 2x squared minus x minus 1. And then this time we're concerned about the x values -4 to +4. I graph that. So I see between -3 and -2, there is a 0. -1, 2, -3, and -2, and then -1 and 0. And then finally between 0 and 1. So 3 zeros on that interval, and they're between these 3 sets of 2 consecutive integers. So we're not stating exactly where they are, we're stating which consecutive integers are they between. And in this case, it's these 3 sets. Okay, so graphs that approach infinity. So if you look at this graph, we're going to use the graph to describe the end behavior. In other words, and this is a new, probably a new way to write it for you, we're going to use limit notation. So we're going to say the limit as x approaches infinity of f of x, and that will be its behavior as it goes in this direction. And we see it goes up, up, up forever. So we're going to say the limit as x approaches infinity of f of x equals positive infinity. And then let me write this a little better. So it should kind of look like this. And then the limit as x approaches negative infinity of f of x is what happens as x goes in a negative direction. And we can tell from looking at this graph that it's going to go down, down, down forever to negative infinity. Okay, moving on. Here's one for you. Try to describe the end behavior here. Pause the video and come back when you think you've got it. Okay, so if you're back, here's our graph. Once again, the limit as x goes to positive infinity of f of x equals positive infinity. And the limit as x goes to negative infinity of f of x equals negative infinity. So those are descriptions of the two end behaviors of this function. Example 5, graphs that approach a specific value. So it doesn't have to go to infinity as it gets bigger and bigger and bigger. It can approach a certain constant value. So use the graph to describe the end behavior here. So we're going to need to go in a really big positive and negative direction to understand this graph. We go to y equals, punch in x plus 2 divided by x squared minus x minus 2. Oops. There we go. So x squared minus x minus 2. And then we hit graph. So I can kind of see what's going on here. But I need to zoom out. So let's zoom standard first. This is negative 10 to positive 10. That gives me a much better idea. Do you see how the line gets really flat? In other words, it approaches a certain value. And in this case, it's approaching the x-axis, which is y equals 0. And if I punch in some really big values here, if I go to my table and scroll down, 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 you see how those numbers are getting smaller and smaller and smaller. And if I did that in the other direction, you would see the same thing. So it's going to get smaller and smaller and smaller. In other words, the limit as x goes to positive infinity of f of x equals 0. It approaches the x-axis. And the limit as x goes to negative infinity of f of x is also 0. To the left, it also approaches the x-axis. And supporting the conjecture numerically, we could choose a value very large. So let's say f of 10,000. And then for the negative, we'll choose f of negative 10,000. And if we're right about this, these will be very close to 0. And they might even be so close that the calculator can't even tell the difference. So let's have our table start at 10,000 here. And we see that's 0.00004. Well, sorry, 0.0004. Real close to 0. And then if I have the table start at negative 10,000, it's negative 0.004. So that supports our conjecture because those numbers are very close to 0. And if I went even larger, like 100,000, it would be even closer still. Never quite get to 0. Just approach it infinitely. Okay, so here's one for you. Take a second, pause the video, work this out, and then come back and we'll see how you did. Okay, so I have f of x equals 2x minus 1 over 3x plus 2. We want to describe its end behavior. This one will be a little more interesting than going to 0. So if I look at the graph, and I'll have to change it to 2x minus 1 divided by 3x plus 2. It kind of looks like maybe it's going to the x-axis, but no, it's not. It's just above it. And if I start looking at some really big values, once again, if I go to the table set, and let's start at positive 100. If I look at some really big values, it's 0.659 and 0.66. And what's actually happening is it's getting closer and closer and closer. And if I put in a really big number, maybe it'll be a little more obvious. Let's do like 100,000. It's getting closer and closer to 2/3, 0.6666, and so on forever. So the limit as x goes to positive infinity of f of x, in this case, is 2/3. And then the limit as x goes to negative infinity of f of x. Well, let's try some really big negative values. If I go to my table setup and punch in negative 100, I keep going in a negative direction. See, we're approaching the same value, but from the top, from above this time. Okay, so let's put in a really big negative value. You see, there we go. The same thing, 2/3. It's getting closer and closer to 2/3. We'll never quite get there, but it'll get arbitrarily close. That's the thing about a limit that's kind of confusing. It does something forever without ever accomplishing it, approaching a value. Okay. So here we have the symmetric energy function. E equals x squared plus y squared over 2. Y value is held constant. And what happens to the value of symmetric energy when the x value approaches negative infinity? So this y value is held constant means effectively I can plug in any constant value. I'll just plug in 1. And it won't make any difference. So I'm concerned about the behavior of this relationship as x goes to negative infinity. So if I plug this in the calculator, x squared plus 1 divided by 2, and I'll graph it here. I can tell by looking, as we get higher and higher and higher, x is going to go up, up, up to positive infinity, but we're concerned about x approaching negative infinity. So to the left, I see it does the same thing. So the limit as x goes to negative infinity of that capital E function equals positive infinity. This is the solution to that. So the illumination E of a light bulb is given by 1 over d squared, where I is the intensity of the light, and d is the distance in meters you are away from the light bulb. If the intensity of a 100-watt bulb, measured in candelas, is 130 candelas, what happens to the value of E when the d value approaches infinity? Well, think about this question. They're asking what happens to the perceived intensity of the light as you get infinitely far from it. Well, of course, it's going to go to 0. But let's show that mathematically. So it is E, different formula, but the same name, equals 1 over d squared. And we want to know what happens if we have d approaching infinity. So this is I, capital I. So this is 130 in candelas over d squared. So there's our function. We're going to change the independent variable to x and plug it into our calculator. So 130 divided by x squared. And if I graph this, it's going to bear out our argument. As we go to the right, you see how it's going really low. And if I punch in a really big value, 1,000 for example, you see it's going to be really tiny, and it'll go closer and closer and closer to 0. So the limit in this case, as v goes to positive infinity, is of e rather. Put the function name in there. Is 0. All right. So I would like for you guys to complete page 30, problems 2 through 12 even. See you next time.